First to IARPC, for those of you, if there's anyone on the call who hasn't participated in an IARPC call before, IARPC is the Interagency Arctic Research Policy Committee, and the purpose of it is to bring together leaders from different US federal government agencies to enhance research in the Arctic. And a major way that gets done is through collaboration teams. And so today, for those of you who it's your first time, this is the atmospheric collaboration team. And so we focus on processes and that help with the understanding of the changing composition and dynamics of particularly the Arctic. And today, we're excited to bring together a group of experts in Arctic wildfire to talk a little bit about Arctic wildfire and in particular, the impact on the atmosphere, or the impact climate change is having on fire, or that fire is having on climate. And we do this to hope to raise awareness within the collaboration team of activities that are going on, and for potential opportunities for interagency collaboration. So we're excited to have you all here. And with that, I think we can go ahead and jump in. And we were discussing just now, and I think we were going to switch up the order a bit from what was on the agenda. So first up, we have Amber Soja, I believe. And so I'll hand it over to Amber.
And I am sharing. And can you see this?
Yes.
All right, great. And so we'll do it from the beginning. My name is Amber Soja, and my expertise is in wildland fire. And I particularly like to focus geographically. I love Siberia, but I like to focus on anything that feeds back to air quality and weather and climate. So I'm going to begin by talking about some of our work that was published this past year in BAM, State of the Climate. And you'll notice many of the authors are also giving talks, or the authors are giving talks. So in the top right, you'll see a buildup index of fire. And what this equates to is how deep and how intense the fires burn. And in the middle portion globe, there's a temperature, the 42-year anomalies. So what we can see is that temperatures and the buildup indices for fire weather are increasing across the Arctic boreal, but particularly in Siberia and in Russia. And you see the same thing on the bottom panels that are graphic, Northern Eurasia on the top and North America on the bottom. So in both panels in June in Eurasia and North America, temperatures are increasing and buildup indices are increasing, but you can see the buildup indices in the lighter graphic, and the dark is the temperatures at 2 meters. So these are increasing even more in Northern Eurasia. And what happens when we have all these temperature increases and also buildup indices that increase is exactly what we're finding. So what is predicted is what is happening. So if you focus on the panel on the left-hand side, that's just the Arctic Circle. And if your eyes move to the middle and the right, we looked at above 60 degrees and above 50 degrees north. So what we find in the A panel in the middle left is that the earliest fire seasons and the largest fire seasons on our record have occurred in 2019 and 2020. And so 2019 was twice the size of the next largest year, and 2020 surpassed 2019 by about 25%. And then if we look at burning this past year in 2021, whether you look at fire detections or burned area products, you can see that the Republic of Sakha, that is about twice the size of our largest state of Alaska, this total area burned the largest amount of burned area on record, of our satellite record. And this is particularly significant. And this time it's not the Arctic, it's all of all of Saka. And this is significant because it is permafrost. So the permafrost thaws, water flows north, that influences the thermohaline circulation. The damage that as permafrost burns down is long term. It's not something that's going to go away in 5 years or 10 years. And it affects the communities and reindeer herds and anyone that lives there. All of their food and their fodder has been burned. So they're going to have a hard time surviving in this next season. So if we're looking at the smoke, because you are atmospheric chemist and scientist, from the 2021 fires last year, I'm showing a 4-panel, July 4th, 27th, 30th, and a zoom in of the 30th so that you're looking at the fire detections and the smoke. And now I'm going to change from the Republic of Saka to the Arctic, and we'll just look at this really quick. So you can see from an Arctic view, the smoke coming up to the Arctic. And it starts to go around the poles, the North Pole, and then it continues. And so this circular motion also takes the smoke and changes the albedo of the atmosphere and could also land on snow and ice. And then I don't have much time, so I hope I'm not going too quickly, but I have so many things that I want to fit in. I want to make you aware of a product that will be released soon. It's a Siberian burned area product, and it's a long-term product. And we've used GAC data because that's the only data that exists now for historic time periods, because we weren't capable of keeping the local area coverage, the LAC data, the 1.1. So this is the geographic distribution of the burned area by 5 years. So you can see that we are getting the Arctic, which is unlike the Modus product that doesn't go that high. So we have the entire area of Siberia and the Arctic. And if we look at this over time and we're able to use Tom's data classify,
Hey, Amber.
Amber, it looks like you're frozen. If you can hear us, I recommend turning off the video.
So you're in the Arctic and you're frozen, which is probably not a bad thing, but we can't hear you.
Do you think we should go on to the second speaker and then give Amber a chance? Oh, wait, is Amber coming back?
I just stopped her video
okay.
on my end to see if it helped.
Yeah.
I will try connecting with her via chat, and I guess I can stop her screen share.
Okay, yeah. So should we move on in the meantime, we think? All right. Let's go ahead then, and we'll jump back to Amber. But next up, we were going to have Piyush, and I'll let you introduce yourself and your talk if you're ready to. Are you ready to jump in?
Sure, why not?
Okay, thank you. Go ahead.
All right, hi everyone. Oh, thanks for the invitation. My name is Piyush Jain. I'm a research scientist at the Canadian Forest Service. So my main area of research is, well, forest fires, but mainly around weather and climate, and looking at trends and fire weather interactions, controls, I guess, weather and climate controls on fire. And I don't specifically look at the Arctic, but hopefully I can touch on a little bit of that today. So I'm just going to share my screen. Sorry, I have 1,000 windows open, so I'm looking for the one which is the right one. Do we see that?
Yes, it looks good.
Here we go. Okay, so maybe I'll just hide this. Here we go. Okay, so I just added the slide at the last minute just to sort of give a little bit of perspective on how fire weather trends are changing across the globe. And I just zoomed in there in North America, which is an area which I predominantly study. So what we're looking at is the 95th percentile of annual vapor pressure deficit trends from 1979 to 2020. And this is using the ERA5 reanalysis to calculate. So you can see that most of the trends in North America are positive, particularly in the north. There's a few negative trends, but across a large band of where we experience fire, there are positive trends. And on the right-hand side, this is sort of the ecozone, or biomes, I should say, delineation that we used in that study. And the light purple corresponds to the polar region, and I guess the medium purple color, I don't know if you can see my cursor here, corresponds to the northern boreal forest. So, and I've zoomed in here on the seasonality. I guess this is what I wanted to emphasize, is that, you know, for the European polar and boreal regions, it's really, this is what you're looking at here is the colored boxes indicate where you have observed area burned in those regions and for those months. So we've colored in the boxes that represent 90% of the area burned annually. So you can see that the season is quite short compared with when you go south. And so, for example, in Europe, the polar region, the fire season is just July and August. And in North America, we're looking at June to September. So why do we care about synoptic fire weather? Well, I just written down a few points here just for the sake of time. I won't go into any detail, but essentially, in regions where you are not fuel limited, weather and climate are the main drivers of area burned. And people have looked extensively at synoptic patterns that correspond to wildfire activity. And one of the main variables that people have looked at are 500 hectopascal geopotential height anomalies. So we'll come back to that later. One of the reasons synoptic scale weather is interesting to look at is, of course, because through numerical weather models, you get a greater temporal period, I guess a greater lead time and predictability than you do looking at surface weather. So there was one study that directly compared forecasts and found that you could get the same error, forecast error in a 10-day synoptic scale compared with a 1-day convective scale. So if we can get a good handle on what synoptic fire weather conditions are, we may be able to improve the predictability of forecasting fire weather. Another interesting aspect here is, of course, there is quite an open debate about what role Arctic amplification is playing in changing of weather extremes and fire weather extremes. Like, is Arctic amplification leading to increased waviness of the jet stream, or is that not occurring? And it's still very much an open question, I think. Some of the newer research tends to indicate that perhaps the jet stream patterns are not changing due to climate change. But right here, I'm going to go into a couple of studies we've been doing, sort of stepping back from that big question and just saying, well, how does the polar jet stream influence wildfire events? So it is useful to first define what we mean by fire spread events. So what I'm showing here on this map is we have a procedure where we take the active fire detections from MODIS, and we superimpose those on the mapped polygons of fires. So we've taken 3 databases there: MTBS, which covers CONUS, we have Alaskan fire perimeters, and then we have the Canadian ones. And then what we can do is we can essentially interpolate those hotspots within each polygon and determine daily fire growth. And then we can determine those days which have the greatest fire growth and call those active spread days. And here you can see the distribution from 2020 to 2016 of all of these events. We identified 9,480 such events. And you can see how they vary in space and how they vary in seasonality. So as you go further north, of course, this sort of corresponds to that diagram I showed earlier, where you get most of the fire activity, most of the fire spread events in the north occurring between June, July, and a few in August, sort of. So looking specifically at the polar jet stream, what we're showing on the left here are the 300 hectopascal wind speeds. So that's near the top of the troposphere. And on the right-hand side, I'm showing the 500 hectopascal geopotential height anomalies. So superimposed on all of these plots are those purple dots show these fire spread events. Sorry? No, okay. So there's two particular dates that I've just picked out here, just because they sort of highlight the very different configurations you can see in the jet stream. So the top two panels show a single jet event, and the bottom two panels show what's called a double jet event, where you have a fragmentation of the jet stream, and you see that you get this high that occurs between the two branches of the jet stream. And this particular second event, I'll come back to this because this is quite interesting from the perspective of Alaska, for example, and other areas in the north, where we did see quite an active fire episode occurring. So what we can do is we can construct these spatiotemporal composites. So we take the meridional flow of the 300 hectopascal winds, and on the right-hand side, we have those geopotential heights again. And what we do is we take each spread day event and we composite those fields, and then we sort of just add them all up. So in each of these cases, the 0 represents, this is longitude and latitude. And it sort of, you composite each field relative to each spread day event. And you do this starting from 20 days before each spread day event to 20 days after. So you can sort of see the mean tendency of those fields and how they build up and decay. So what you see is this red and blue indicates that you have a northerly wind and then a southerly wind. So you have a ridge essentially. You have a large scale ridge, and that is confirmed by the fact that you have anomalously high geopotential heights occurring near the event. The interesting thing here is that you have the buildup occurs over a longer period before each fire spread event, and then decays relatively quickly. And of course, that can be thought of, that sort of intuitively makes sense from the point of view that you are preheating the fuels ahead of the actual spread event. And then we can also break this up by seasonality. So we can do this compositing by month of year. And the main observation, I won't go into detail here, but the main observation is that in the shoulder season, so in April, May, and September, October, the anomalies that you see are larger, but they're also shorter lived. So, and that's what you'd expect in the shoulder season. In the summer season, you have these more settled weather. And in fact, you need smaller, in some sense, you need smaller deviations from the norm to get extreme fire weather than you do in the shoulder season. And then we can also look at differences, broad scale differences spatially. So we can do the compositing by these 3 different zones that I've indicated in the middle here. The main takeaway from this is that the patterns tend to last longer on the west of North America than they do in the east. These patterns are shorter lived in the east. So another way of looking at these synoptic patterns is to look at so-called persistent positive anomalies. So this is a tool, I guess, which is often used to look at blocking events or heat waves. So I'm going back to this example. Actually, this is not 2015 now. This is 2004, which was another active, very active fire period in Alaska and Northwestern Territories. So this is showing a particular date, the June 28th, 2004, where there was a lot of fire events occurring. And you see you have the split split jet stream pattern again. But we're able to track the 500 hectopascal geopotential height anomalies. So this is the idea of the persistent positive anomalies. And this is essentially a heat wave that you're able to track in time and watch the evolution of. So a postdoc that I'm working with, Asim Sharma, has come up with a nice algorithm for tracking these events. And we've done a study relating these events to fire. So one of the things that we looked at is how are these events changing across Western North America? So we've looked at the frequency, trends in the frequency of these events, magnitude, duration, and area. And in fact, interestingly, we didn't find the frequency of the events changed at all. The magnitude and duration changed a small amount, but not statistically significant way. But the area, so the size of the events, is increasing, and that is significant. So that's been submitted right now to the Journal of Climatology, or Journal of Climate, I think. So we're just waiting feedback. And just to finish up, I just thought I'd very quickly discuss the 2021 heat dome, because of course this is of quite a lot of interest. So there's a video here. Hopefully it works. I'll just let it play through a couple of times. So essentially, the red triangles are fires greater than 200 hectares. The orange triangles are less than 200 hectares. Not sure why the legend's jumping in and out, and the blue outline that you see evolving there is that June 2021 heat wave event, of course, which led to record-breaking temperatures in Canada, at least, and I think in Northwest United States as well. So you can see that this very active fire season tracks quite well with the heat wave event. And the right-hand plot, what we're looking at is the size of these different heat wave events as determined by the PPAs that we tracked. And right here, you can see sitting up well above all of the other events from 1979 to 2021, or 2020 at least, is that June 2021 heat dome, June-July event. And what we found was that the event was 53% stronger than other events, 40% larger, and had a return period of 200 years. So it really was a very large, rare event. And right now we're doing some work and reviewing the North American fire season for 2021. And over US and Canada, at least, I can say that had the most area burned, combining the area burned from those two countries, the most area burned for the last 20 years was in 2021, and most of that occurred in July, in the month of July. So yeah, so I'll just finish here with a list of some of my collaborators for this work. And I think I am done at this point. So thank you.
Thank you. I think we'll hold questions for the discussion at the end. And I believe Amber is back with us. Although I don't, oh, yep, I see you now. Welcome back.
She hopes she is. Yes, I'm in the process of sharing. I just hit share. Let me know if you see it.
I see it. And I think you dropped off just as you were introducing your new, or the new product that was going to become available soon. I believe that's what yes.
Okay, so we were on this screen.
It might have actually been 2 after this. There was a bar chart.
Oh, okay. All right. Then we were at the very last slide. So this is just the spatial domain of the 5-year product. And this is the May, June, July, August, September. And the product will be available from 1979 to 2000. So we'll have a full, with MODIS, a really nice long-term view of Siberia to include the Arctic. But MODIS burned area really doesn't quite get to the Arctic. And so I'm really excited about this. And the reason I'm excited is for every reason that you know, with a longer term burned area, we'll be able to look at fire weather and tease apart the connections to fire weather so that we can better inform models and also predict what is going to occur in the future. So I'm really excited about having this long-term database, because we can't do climate without long-term data. And this has been a long time coming, these data, and it's been very hard to put it together. We'll be able to do emissions over a long term from Siberia and from the Arctic. So we'll be able to look at circumpolar fire, circumpolar and boreal fire. So, and we haven't been able to do that before because Siberian data has not been as good as that in North America. And with that, I'm going to stop because I think that I was at the end of my 10 minutes, if that makes sense to everybody here.
Yeah, you were able to complete. We have a few minutes if there was more, but if that was the end, that's very good.
Okay, all right. Yeah, I don't want to read the screen to you, but yes.
All right, sounds good. And as Meredith put in the chat, if you have questions for the speakers as we go along, you can go ahead and put them in the chat and we can come back and address them during the discussion session at the end. And next, I would like to move on to our next speaker, Bhatt, and she'll be talking to you a little bit about an EPSCoR project. So take it away.
I am muted. Hopefully you can see my screen. Hi, I'm Bhatt. I'm an atmospheric scientist at the University of Alaska Fairbanks, and I do a variety of climate-related work. I can't even figure out how to categorize myself anymore, but I'm representing a team of researchers working in boreal fires component of the Alaska EPSCoR Fire and Ice Project. The middle photo shows 2021 Munson Creek fire that occurred just outside of Fairbanks, burnt 22,000 hectares, and was one of the biggest fires of actually a very quiet season in Alaska. It was near the Chena Hot Springs Resort, and it came close to homes and cabins. And the photo on the left is the Yankovich fire, and that occurred in July of 2021, and it was close to many homes in Fairbanks, and it actually was on forested area that belongs to the University of Alaska Fairbanks. So that was, it was very close. You could see it from our homes. It was put out very quickly since the fire crews were in town, and there's some really good visuals of smoke jumpers landing in the nearby muskox farm with musk oxen staring at them. Now, the study of wildfire in Alaska is motivated by the cascading impacts of climate change on fires, as seen in this time series of acres burnt each fire season from 1950 to 2021. The shaded areas show the 33rd, 66th, and 90th percentiles of area burnt, which are increasing over time. Beyond acres burnt, fires have impacts on ecosystem services, human health, safety, economy, really so many other aspects of life in Alaska. Today, I'm going to highlight what we're doing regarding climate drivers, and we'll briefly touch upon fuels. The fire triangle on the right identifies the three elements needed for fire: weather, ignition, and fuels. And our research aims to make the most skillful possible seasonal outlook for lightning, fire weather, and developing the best possible fuel map so we can put all this information together for fire managers ahead of the fire season. And the current project ideas emerged from the extreme 2015 fire season. And we're sitting around preparing a proposal, and we're talking to Alaska NOAA forecasters and managers. And so NOAA initially funded this work to develop seasonal forecasts of fire weather in Alaska using the North American multi-model ensemble forecast that just became widely available. And we use that to calculate the Canadian fire weather indices, the buildup index, which Amber's already shown. And then this work was expanded under the NSF EPSCoR project. And the fire season in Alaska has 4 distinct subseasons. And the focus of much of our work is the so-called duff season, when the seasonal maximum of the buildup index, shown here in gray, reaches its maximum. Lightning strike counts are highest in this duff season, as well as the MODIS counts. So it's the most impactful season. So we're focusing our forecasting first on trying to get that right. And the buildup index, as Amber had mentioned, is it measures the readiness of fuels to burn, and it was developed by the Canadian researchers based on statistical relationships for the boreal forest, and it's used operationally in Alaska. So, and it's very different than the one used in the lower 48 for identifying fire risk. And the fuels in Alaska are largely in the, not totally, there's a lot of fuel in the ground, and these are shown by the Duff plug here. And so as part of developing our research proposals, we're put in communication pretty early with fire management, and that guided the questions we focused on. A key need identified by fire managers was summer climate information in March to help make decisions about allocating resources for the upcoming season. The publicly available seasonal forecasts were perfect to apply to buildup index in order to come up with a seasonal forecast. And what we're doing is we're creating these forecasts for using the NOAA CFSV2, the European Center model, and the Meteo France model. Here's some details about how the models are calculated. I won't go into details, but I wanted to put this slide in so you have the information. And the first step is to evaluate the 1994 to 2019 hindcasts of all these forecasts. And then we made forecasts live for 2020 and 2021. And we know from past work that we've done that you really need to correct the temperature and the precipitation of the seasonal scale to improve your skill. And we use the models individually to create a forecast, and then we combine them into a multi-model ensemble, which helps improve our skill. And we create categorical forecasts. So we say BUI is going to be above normal, below normal, or average. And we do this for regions called predictive service areas, and that's what are the regions used in fire management. And this figure shows us the forecasts that were presented by PhD student Cecilia Boris-Striegel in 2020 and 2021 for each of the individual models, as well as the multi-model ensemble. And on the right here, we see what the observed were. And again, these were 2 years with fairly low fire seasons. And there was some skill, it was more skill than I thought there would be, but kind of the next step is how do we improve the skill? And the other thing that Cecilia does is she presents to fire managers in fall and does a post-mortem of how the forecast did. And this has been helpful in figuring out how to present the data, as well as thinking about where we have the most issues. And I guess one thing I can say is that the forecast errors are primarily associated with temperature errors. It's not universally true in all the different regions, but that is one of the common conclusions we have. Now, we want to increase the forecast skill by advancing our post-processing of the forecast. And we really don't have a clear answer on what are the seasonal climate drivers of summer weather, or whether there's even any predictability at that scale for summer weather. So we tried to hire a postdoc to work on this, and partially, I'll make a long story short, because of COVID delays and because of visa issues, we ended up pivoting and created what I'm going to affectionately call the Frankenstein postdoc. And what we did is we took a diverse group with people with diverse skills in climate variability, modeling, remote sensing, and computer science at a variety of different levels. We have early career faculty, postdocs, fire management, Alaska climate expert Rick Toman, and students. And so we work together to brainstorm and really prioritize topics on how to attack this problem. And we created a patch for each team member. So everybody has their own piece of work, but they're working together. And we're focusing on the predictability of the timing of snowmelt, the Duff season temperature and precipitation, lightning likelihood, and the timing of the end of season rains. So when the rains come in August, late July, early August, that shuts the fire season down. So we have any predictability. And again, this was done in conversation with management. And this information is being analyzed to help us improve the seasonal forecasts. And we're using a variety of statistical methods as well as machine learning. And the goal is to use this information to improve the seasonal skills. So More fires are started by humans in Alaska, but more acres are burnt due to lightning ignition. So investigating the predictability of lightning, which at first glance may seem insane, but I think there are things that have been identified that can give us some sense of lightning likelihood. And the work we've done so far shows that if you analyze lightning strokes, the observed lightning strokes with reanalysis data on a seasonal timescale, convective precip is one of the key parameters identified to help predict what the likelihood of lightning. On an hourly time scale, we've work done by master student Jonathan Christ found that upper level winds, and Piyush talked a lot about the upper level, which is really important. At hourly timescales, upper level winds in the Tanana Valley Predictive Service Area, which is right around Fairbanks, really determine the likelihood of lightning strokes. And what this suggests is that the direction of the storms help set up conditions that are more conducive for lightning, and potentially those types of patterns are predictable. So to understand this further, our master student Josh Hostler is categorizing synoptic weather patterns, and he's associating the strokes per day according to lightning. And what he finds is some synoptic patterns are more conducive to lightning. And so and I'll finally briefly mention the fuel work that we're doing very quickly, because it's the third component of the fire triangle, and fire managers identified the need to improve the Alaska fuel map, which they're using operationally to run fuel spread models. And part of our team has been working actively on using ground validation and a variety of remote sensing instruments and data to develop these new fuel maps. And this just gives a quick highlight of what work that's been done. And so I'm speeding to the takeaway points, and really our final goal is to produce a seasonal outlook that this is our vision, that combines the seasonal climate information, the lightning likelihood, and the fuel conditions. And one thing I didn't talk about is we have folks on our team looking at fuel moisture as well as vegetation state due to insect infestations. And, user-inspired research is approached very differently than if this had been purely curiosity-driven. And in 2021, the fire managers asked if we would repeat what we're doing for the March forecast with the May forecast. And honestly, if we'd done this work, had been less user-inspired, we would have probably started with the May forecast since it's much closer, a shorter time scale. We would have expected more skill. So we kind of attacked the harder part first, and now we're hopefully doing what's more skillful. And these types of collaborations really require purposeful meetings among diverse folks. So the fire managers attending our meetings has really been, critical to how this is all developed. And this takes attention and energy, but I really think the payoff is amazing. And boundary organizations are really essential for facilitating this user-inspired work. And the Alaska Fire Science Consortium team were there from the beginning to really help us make connections between people and with ideas and translating. And I guess kind of my key take-home message that this kind of user-inspired work, a real key to making science actionable is it takes time to work well, and it takes strong team science framework. Thank you for your attention.
Thank you, Uma. With that, I will open up the floor to questions for our speakers. I did see from before there was one question in the chat, and I can go ahead and start with that one while people get lined up. But Adrian asked, does Siberia have good historical lightning data? And I believe this was put in the chat when Amber was speaking. So I believe it is directed at Amber.
I'm going to say that I don't think so. If there is good lightning data, it would be satellite based, and it would be the data that we have as well. I don't work with lightning data, but it's still critically important because it is a boreal Arctic system. Although still a lot of the ignitions are by humans, like everywhere. So I would leave that for somebody who looks at lightning and this type of data. So that actually might be Uma or Piyush.
I've asked that question and I don't have an answer. I don't know. I'm going to throw it to Allison York. Allison, do you have any thoughts? Or maybe Piyush does.
Yeah, well, I'll start and Piyush can come in. My understanding is that there is data, from the Global Lightning Mapper, which is a satellite-based system, but that it's not great, and especially it's not great as you go further north. And the other thing is that there's good evidence, and Rebecca Schulten, I believe, is on this call and maybe can speak to this, that especially in the last couple seasons in Sakha, that a lot of the ignitions actually were overwintered, especially I believe from 2019 to 2020. Looks like that was a big source. But Amber's right that a lot of this is human ignitions, I believe, on the ground.
Yeah, I can't really add anything. Not familiar with lightning data for Siberia, but in North America, we use the Vasella proprietary network and we get very high quality data. We have agreement, I guess, NASA and Canadian Forest Service here, we have agreements that we're able to get our hands on that data, but I guess you have to rely on satellite observations for Siberia. I know the new GOES supposed to have a good lightning detector, I think, sensor on there, but I don't know how well that works up north, being a geostationary satellite. So.
Okay, it looks like we have another question in the chat. Does anyone have estimates of CO2 emissions from the 2021 fires?
I think I haven't done, I think you're talking about the Republic of Sakha. So I haven't done an estimate, but I think that they would be relatively easy to do. The thing about those fires in 2021 in the Republic of Sakha is they burned down. So as they continued to burn, they just burned down. So I think that we could estimate it, and people probably already have. And we could do a back of the envelope estimate, knowing how much fuels are there. And we do know that, or that were there, as the permafrost burns down and thaws and burns. But I think that the best way to get the answer is to have boots on the ground and to have somebody measure the depth of burn. And I haven't done that. I know Sander Becky, I probably have his name wrong. He had plans to go there in 2021, and I was going to go with him, but I didn't follow through, and I don't know that he went.
Perhaps I can just speak to the Canadian side of things, which is we do come up with estimates of emissions, but this is somewhat delayed by the fact that we have to have all the procedure that we have in place is we have all the fires mapped first, and there's a delay of about a year before we get that data because it's quite an extensive process. So we're sort of like the carbon accounting that we do for fires is about a year in arrears. So we don't have that for Canada. We don't have that data yet, but I guess in end of 2022, we might know what the emissions look like for 2021. So.
All right, it looks like we have another question in the chat from Tony Chen. May I ask when the pre-2000 burned area map for Siberia will be out and where it will be out? I just want to make sure I know where to look. And this also, is the spatial resolution 1 kilometer?
It is not 1 kilometer, but it will have all the bigger fires. And the reason that it's not, well, first our target journal is the Journal of Remote Sensing. And we will upload the data at the same time so that the article and and also the data will be available. And we're really ready to be done with this because it's been a long time coming. But the GAC data is all that was saved. So there were no downlink stations in the Soviet Union. And so the satellite data wasn't saved and there wasn't enough space. So instead of the 1.1 kilometer AVHR data at Nadir, what happened is they took the mean of 4 pixels, so 1, 2, 3, 4 pixels, the mean, skipped 1, and then skipped 2 lines. So for those 15 pixels, you have the mean of 4. But because most of the burned area is by large fires, you have you capture all the large fires. And I believe, if I'm not mistaken, we did capture one fire that was 22 square kilometers, but that was an accident. And the other problem with this historic data that is really a challenge is Landsat data. There wasn't a lot of Landsat data to verify with. There was more before 79 than from 80 to about 87. So we just did the best we could, and it's the best only game in town is using GAC data if you want to do something really detailed. And for timing, we use TOMS, the aerosol index, in order to know when the fires were actually burning. Sometimes we did get smoke from the active fires as well. So we used everything we could in order to get the timing right for these fires. It's a really neat data set. I'm really proud of it.
Thanks, Amber. Other questions from the group? I was just going to ask Uma, you talk about with user-inspired work, how figuring out how to have good meetings is critical. And I was wondering if you had any, advice for people who maybe don't start out with user-inspired work, but think their work might be useful in some way, if you've had any lesson learned throughout your process that you wanted to share.
I guess scientists, we're often sometimes not patient. We want to kind of charge ahead. And I think it really forces you to slow down and be patient in figuring out what you're going to do. So I think personally, if you're being patient about it, it makes things go more smoothly. And I think in general, I guess what I encourage my students to do is work on their people skills, because your people skills really do come in handy when you're working in a group to get something done. So the golden rule, remind them of the golden rule. Yeah. But I can't think of anything too deep other than patience and the golden rule.
Colleen, can I speak to that, please?
Please do, please.
Yeah, I think that, to be honest with you, I think you're framing the question a little bit wrong. I don't think the onus on this should be on the individual scientist. I think this is a question for funding agencies and for the overall structure of how science is organized. Uma's absolutely right that the incentives for the individual scientist are to get papers published and students finished and grants funded as rapidly as possible. And I think that funding agencies, if they want to get science done that can be operationally useful in the real world, need to lengthen their funding cycles, need to fund boundary organizations, need to take a different view of how science is used to benefit society. It's not, I'm not arguing that research is not important. Research is very important, but we need to put more resources into how existing science gets used on the ground. That's my 2 cents.
Thanks, Allison.
Sure.
All right, do we have any other questions? I want to leave a few minutes for updates from the team. So I'll take last call for questions for our speakers. And I'm assuming your hand is for your previous comment, Allison. And if not, I'll assume it is. If there are no other questions, I want to thank our speakers very much for your presentations. And we'll end the meeting with if anyone has an update to share with the group.
Hey, Jack, Dib, or anyone else up in Alaska for the alpaca experiment? Do you want to give us an update?
Well, we're in our final week, right? We've been running, most groups have been up and operational since the 17th of January. And we're going to stop on Friday, or people that are doing filter sampling, maybe Saturday morning. It's been kind of interesting. And right now it's a really weird February. It's like very warm. They're forecasting freezing or very close to freezing temperatures the next few days. And it's snowed a lot, maybe a record amount of snow in February. So it's been a real range. So I think things are going really well.
Thanks, Jack. Any other updates from we still have a few minutes?
There's one in the chat. Richard is noting that the modeling team is having a meeting that might be relevant to many people in this group on atmospheric composition forecasting with the NASA GEOS-CF system tomorrow at 3 Eastern.
Thank you, Richard. Yeah, looks really interesting. It's a global model that NASA has been developing over the last decade, and it's assimilating a lot of satellite data, but I guess it's at 25 kilometers globally. Maybe it's even, I'm thinking if I'm remembering correctly, CF stands for composition forecast.
That's right. I can't remember what the resolution was, but at one time it was the highest resolution composition model out there.
Right. It's a arms race going on out there between all the different global models. Other announcements? Colleen, do you remember what our next topic is? Just advertising for the March meeting?
I believe it will be something around Arctic amplification, if I am remembering correctly.
Yes. I can't remember either. So if that means we don't have speakers yet, that Colleen Heiss and I will be busy twisting arms over the next month. But if you know of someone that would be a great speaker, don't be shy and email us.
Yes, Arctic amplification is what is on the schedule.
Okay,
Thanks,
very
Meredith.
good.
You always keep us on track.
All right, if no one else has anything else, I'll say thank you again, Meredith. I don't know if you have any last announcements to make.
Just one, and that is that the Arctic Research Plan, the new Arctic Research Plan is out the door. Probably a lot of you have already seen it, and we're currently getting into the weeds with the Arctic Research Plan and developing some implementation. So there's, I put a link in the chat, and there's a place you can go through this link to submit anything, any relevant research activities around the new Arctic Research Plan. So just leave that there. And the recording for this meeting will be posted on the IARPC website. And thank you. This is a great meeting.
Thanks to you all for listening. It's nice when the Arctic and Siberia are important.
Thank you, Amber. You have to come back to our, we're always talking about the Arctic in these meetings, but appreciate your persistence coming back after getting kicked out.
Yeah, that was weird. Thank you.
Bye, everyone.
Thank you, everybody.
Bye all, thanks.